My name is Leonid Ponomarenko. I'm from University of Lancaster and from University of Manchester, both at the same time. I'm chairing this session today, and the first speaker today I'd like to announce Alex Hamilton. And he will be talking about electron superfluidity in electron-hole bioreactors.
Thank you. And I'd like to thank the organisers for arranging such a splendid venue and giving me the chance to come back to Camerino. It's always a pleasure to be here. So I'm going to be talking a little bit about some mainly theoretical work that's been done by Andrea Perali and David Neilson. And they're wonderful theorists who are rooted in the abstract with their feet planted firmly in the air. And it's my job just to make some contact with reality every now and then. So that was really my role. And so I'm going to talk a little bit about electron-hole superfluidity. And it's a great shame that Yuri couldn't be here, but this is really follows on from his seminal work. So I'll talk about the history of the search for excitonic superfluidity, the double monolayer graphene system, which I want to propose as a new hope. Our work on quadratically dispersing atomically thin crystals, and then possibly, if there's time, just back to why it's so hard to do this in the gallium arsenide material system that's been so well studied. So there's been a long-standing interest for more than 35 years now in electron-hole superfluid condensate in the solid state. And the idea is that whereas in ordinary superconductors you have a phonon coupling between your electrons, if you can take an electron-hole plasma with a very strong Coulomb interaction and prevent the electrons and holes from meeting and recombining, then you can form an excitonic Bose-Einstein condensate, which should be a superfluid, a chargeless superfluid. So this prediction was made some time ago by Yuri Lozovic. There has been a long search to try and realize this apparently simple system. And some of the earliest work uses gallium arsenide, aluminium gallium arsenide double quantum wells. So you make a heterostructure, you form two quantum wells, you dope one of them n-type, so you have electrons here, you dope the other quantum well p-type, so you have holes here, and then you try and get excitons to form between the two wells. And when the distance is quite large, several hundred nanometers, the Coulomb interaction is too weak, and so the excitons don't bind. If you try and reduce the separation between the electrons and holes, you've got a p-n junction, and anyone, your undergraduate will tell you that there's a depletion length, a finite depletion length for a p-n junction, and so as soon as you try and bring these two things close to each other, the electrons and holes recombine, and there's nothing left. Uri Sivan at IBM in 1992 came up with a very elegant solution, a very complicated device, where he could make separate electrical contacts to the hole layer and the electron layer, and he'd applied a large bias between the two. So now he brought the electron quantum well and hole quantum well to different energies, brought the system to flat band to get rid of the depletion length, and if you apply about 1.5 volts across a distance of about 100 nanometers, less than 100 nanometers, so you're very close to the dielectric breakdown, then you can form separate electron and hole. And his idea was to pass a current through one layer and then measure the drag current in the other layer. And if the superfluid forms, electrons and holes combine, and you get a perfect drag. So this would be an absolutely clear signature of superfluidity. So this was work done in 1992. Unfortunately, his contacts failed below 9 Kelvin, and so he was unable to observe the exciton formation. And the challenges are that you want to get the layers close to each other, so you want a small layer separation D. You want the particles within the layer to be quite far apart, so that an electron in one layer feels the hole in the other layer, but doesn't sense another electron nearby. So you really want compact pairs separated by a large distance from the next pair. And obviously, if the particles are very far apart, they're rather dilute, you want to have low carrier densities. That means you need low disorder. So for 20 years, solid-state experimentalists have been working on this, particularly at the Cavendish Laboratory in Cambridge, where I was for many years. And I have watched postdoc after student after postdoc being hurled at this problem. It was like the Eastern Front. The best and the brightest young went over the top, and we still don't have superfluidity. The temperature now has been reduced from 9 Kelvin to 0.05 Kelvin, so we've gone down a factor of 200. I should make it clear that I'm not involved in those experiments. I was too cowardly to go over the top. The distance between the layers has now come down to about 25 nanometers. The barrier between the two layers is 10 nanometers. The minimum carrier density has gone down to 4 times 10 to the 10 per centimeter squared. And what is seen now, if you look at the drag resistance, or the amount of drag that is carried from one layer to the other as a function of temperature, initially you see a decrease due to phase space arguments. I think it's T squared as you come down. And then possibly there's evidence of a slight upturn as you get to very low temperatures. And I can return to this because there's some controversy over this upturn. So there are hints for the exciton superfluidity, but it still hasn't been observed.
Sorry, but is there any rough estimate of what superfluidity is?
Yes, there is, and I'll come. It's a few Kelvin. I'll come to that right at the end. So, I mean, this is well below T6, the predicted T6. The problems with gallium arsenide that the experimentalists face are that the quantum well has a finite width. It's about 10 nanometers wide. So the distance from the center of this wave function to the center of this wave function is at least 10 nanometers. You need to have a barrier in between to stop the electrons and holes recombining. That also needs to be about 10 nanometers. So your center-to-center distance is at least 20 nanometers. And the reduced Bohr radius is 12 nanometers. So you're sort of 2 reduced Bohr radii away. On top of that, the bands are rather asymmetric. The hole mass is about 5 times larger than the electron mass, which makes it difficult to nest the Fermi surfaces. So these are all challenges, and there's a very nice review article by Kanti Gupta describing some of the work that has been taken over many years to try and realize this superfluid. So there's no evidence for superfluidity in gallium arsenide. We need to get the distances down and go to lower carrier densities. Then there's a very elegant proposal from Alan McDonald that maybe you could see room temperature superfluidity by using graphene. Electrons in one layer of graphene and holes in another layer, and you separate them by some distance. And graphene's a beautiful system. It's atomically flat, so you immediately get rid of the finite thickness of the quantum well. The layers are strictly two-dimensional, so that the width is approximately 0 nanometers. It's a zero-gap semiconductor, so you don't have to apply this huge 1.5 volts over 100 nanometers. So the electric fields you need are much, much smaller. Because you need smaller electric fields, you can make the barrier between the two layers much thinner. Then another breakthrough, the hexagonal boron nitride makes an absolutely beautiful barrier. You can put that between the two layers. You get very low disorder, practically as good as vacuum. You have a very large band gap, much larger than the gap in aluminium gallium arsenide. So you can get down to barrier thicknesses of order 1 nanometer. And you have near identical conduction and valence bands. So there's no mismatch between the electron and hole Fermi surface. So this is the ideal system for studying cases looking for superfluidity. But there are some disadvantages. Nature doesn't like linear dispersing when it comes to bound states. If you have something with a linear dispersion, it's like light. There's no bound state. So it's difficult to form the excitons because the carriers are essentially massless. The interactions in graphene are weak. The RS for graphene is almost independent of density. It's 2.2 over the relative dielectric constant kappa. So you can't turn up the interaction with the state. So some calculations by Yuri Lozovic a couple of years ago. He plotted the predicted superfluid gap as a function of RS, which is the ratio of the particle separation to the Bohr radius. And his results, when he includes screening, are that you need to go to RS greater than 2.3, and then you'll form the superfluid. There's a sudden jump in the superfluid gap, and then the superfluid is very easily observable. And he said, look, this is trivial. All you have to do is simply reduce kappa below 1. And while this is certainly theoretically possible, I don't know any way of doing it in this universe unless we do something very, very clever with metamaterials. Relative with dielectric constant less than 1 is a little bit challenging. So in reality, we're always stuck on this side, so observing the electron-hole superfluid could be difficult. And in fact, there was some beautiful experiments out of the Manchester group. They made two monolayer graphene samples, separated them by a ridiculously thin barrier of only 1 nanometer, looked at the drag resistance between current electrons flowing in one layer and holes flowing in the other, and they observed beautiful t-squared behavior down to the lowest measurement temperatures, and no evidence again of excitonic superfluidity. But it does point the way. The trick is, don't use systems that have finite well widths. Don't use systems where your barrier between the two is small. So can we use this idea, but with a different material system? So the idea that David and Andrea came up with is to use quadratically dispersing atomically thin crystals. And so now if you have a quadratic dispersion, for example, here's the dispersion of monolayer graphene with its linear dispersion. If you take AB stacked bilayer graphene, you get at intermediate energies at least quadratically dispersing bands. So you have a well-defined rest mass, and you can form excitonic bound states. If you apply an electric field across the graphene, you even can open up a small gap. Because it's graphene, you can keep your hexagonal boron nitride dielectric, so you can still get the layers very close together. They're very, very thin still. They're still only a fraction of a nanometer thick. So now you've got a system where you can get them very close together at low density, and in fact there's already been demonstrations that you can get to very low densities in bilayer graphene. So all of these are very promising. So this is the proposed system. Take two parallel bilayer graphene sheets. So each of these is now bilayer graphene and bilayer graphene. And you separate them by a dielectric, for example, hexagonal boron nitride. Within each of the sheets, the carriers are hybridized across the two sheets, and you form a single conducting sheet. So you have electrons in one layer, you have holes in the other layer. You have metal electrodes above and below, so you can control the density within the layers, and you have separate electrical contacts to the two layers, so you can even apply a bias between them, or you can pass a current in one layer and measure the drag in the other. So theoretically it's very simple. Experimentally making such things is a tremendous challenge, which I have no ability to get involved in. But from the theoretical point of view, now we have a very big, nice system. We have quadratic energy bands, at least for densities above about 10 to the 11 per square centimeter. The Fermi energy in each sheet now just looks like an ordinary semiconductor. So RS, the ratio of the Coulomb to the kinetic energy, just goes as 1 upon the square root of the density, and you can reach the strongly interacting regime. In fact, in existing bilayer samples, RS has already been reached as large as 9. So we can get now to strong interactions in an ideally thin system. And the next challenge was one that I don't have to be involved in. Andrea and David basically solved the mean field equations for the chemical potential and the superfluid gap, delta K, which is the maximum gap at some K. So I won't go through the equations. There is one slight complication, and that is when solving these equations, how do you deal with the Coulomb interaction of screening? Your Coulomb interaction, you have some screening to put in, and the question is, how do you deal with this? One approach is just to ignore screening altogether. Another approach is to say, well, we know how to deal with screening in normal Fermi liquids, so let's just put that in. And the third approach is to put screening in the superfluid state. And there's been some discussion over the last 5 or 10 years about this, mainly because these three approaches give answers that vary by more than 6 orders of magnitude, which, if you're trying to make contact with reality, gives you plenty of leeway, but isn't a very good guide to experimentalists. Very recently, there were diffusion quantum multiplier calculations by Richard Meads and Maizano, and they've done calculations for quadratically dispersing systems with matched dispersions in the electron-hole system, and they've calculated, including essentially exactly the screening, what the condensate fraction in a superfluid bilayer system would be as a function of RS for different values of the spacing between the layers. And this d is in units of the Bohr radius. So if the two layers are very close together, what you see is at very large RS, essentially you have electron-hole pairs that are very far apart. So all of the Coulomb interaction is between the electrons and holes, and there's only a very weak dipole-dipole interaction between the pairs, and so you just form the excitonic condensate. And in this regime, screening really doesn't matter. There isn't anything to screen. The electric field lines are just going between the electrons and holes. As you reduce RS, the electron-hole pairs start to come closer together, and now screening matters. And which approximation you take is going to give you a very different answer for the condensate fraction. So if you don't include screening, the condensate fraction drops gradually, and then there's a sort of rather large drop with RS less than about 1. If you include screening in the normal state, then it comes down very smoothly, and the DQMC calculation predict it comes down gradually, and then there's a very sharp drop, which would sort of signal the transition from the Fermi liquid state to the superfluid state. And mean field calculations with screening in the superfluid state agree reasonably well in terms of they produce this very sharp drop as well. If you do the same calculations now for making the layers further and further apart, as you pull the layers further apart, the critical RS that you need in the DQMC increases slightly. The difference between the normal state screening, the unscreened and the superfluid state screening becomes larger, but all of them essentially agree that at large RS you get basically just the bosonic state, and then as you make the transition to the BCS state, the screening turns on and kills the superfluid. You can calculate essentially what the phase diagram looks like as a function of the layer separation D and the RS, which is the reduced particle spacing. This is for 0 condensate fraction, and this is for 25% condensate fraction. Because the unscreened and the normal state screening don't have a sharp transition, it's difficult to identify where exactly to take the superfluid transition from 0. So let's just look at 25%. And what you see is that if you're at very large RS and very small layer spacing, you have the superfluid state. And then as you decrease RS, or as you increase the layer spacing, you make a transition to the normal state. And these are the DQMC results. This is the unscreened interaction, which overestimates the maximum carrier density that you can have before you make the transition to the normal state. This is the normal state screening, which is rather pessimistic. And the superfluid state screening is in reasonably good agreement with the diffusion quantum Monte Carlo. So this suggests that you should calculate screening in the presence of the superfluid, and it generates slightly conservative results, but in reasonable agreement with Monte Carlo. So now what we can do is we can calculate the energy gap delta and the transition temperature Tc for the superfluid state formed, and then answer the question, do we think that you can realistically observe the electron-hole superfluid? So this is delta max, the maximum gap, as a function of the 2D carrier density. This is plotted with screening in the superfluid state and unscreened. And this is done for 2 different layer thicknesses, where the layers are separated by a 1 nanometer barrier, which has already been demonstrated for the monolayer graphene, and for a 0.5 nanometer barrier, which is possibly a bit more challenging. And then what you see is that as you reduce the density, you make a transition. If you start at very low density, we don't calculate what's happening here because the bands are not quadratic. At very low density, you have the excitonic pairs. As you increase the density, the gap goes up slightly, and then there's this very sharp drop as the screening turns on, and the screening basically just fills the superfluid. If you look at what the gap looks like as a function of K upon Kf, then here at point P, you have a very broad plateau, and that indicates that you're in the BEC regime. As you increase the density, you bring the pairs closer together, and you expect eventually a transition to the BCS regime. But what you see is over this range, rather broad range of densities, there's still no evidence of BCS transition. Essentially, as you approach the BCS transition, the screening turns on and kills the superfluid. So even when you go relatively close to the transition, this peak in K is centered on K equals 0. So now we can construct something like a phase diagram for the two bilayer graphene. This is the TC max. This is the 2D carrier density. At very low densities, bilayer graphene doesn't have quadratic bands. It has linear bands, so we won't worry about what's happening there. The TC max that's being generated here is enormous. It's several hundred Kelvin. So you might hope for a superfluid with a transition temperature of 700 Kelvin. But of course, it's a two-dimensional system, and what determines the melting temperature is the Cusseler-Staulis transition, and that just goes as superfluid stiffness, and that essentially increases linearly with the carrier density. So you have a region here with a superfluid. At higher temperatures, you end up with a pseudo-gap regime, and then once you go above this NC, screening kicks in, and you end up back up in a Fermi liquid. For a 1 nanometer barrier, just to give some numbers, the TC maximum, which is here, just before you make the transition to the Fermi liquid, is 21 Kelvin. And I should reiterate that these are slightly pessimistic numbers. The DQMC gives slightly higher numbers. And the critical carrier density here is about 5 times 10 to the 11 per centimeter squared. So that's already considerably higher than has been achieved in bilayer graphene. So this is definitely achievable. So there should be strong signatures of the superfluid below TC, which should be seen in Coulomb drag and interlayer tunneling measurements. There should probably also be signatures in the compressibility. But even above TC, there's an opening of a pseudo-gap, and that may also be detectable as deviations from standard Fermi liquid behavior. Up to, well, delta K is rather large, so it may be detectable up to room temperature. And of course, this concept is not limited to just bilayer graphene. It will work with any quadratically dispersing atomically thin crystals. And in fact, as we pointed out, so here's our phase diagram, and there's a very recent preprint from Fogler and Butov in UCSB, and they've considered essentially the same system, hexagonal boron nitride dielectric, but instead of using bilayer graphene, they use molybdenum disulfide, which is an ordinary quadratically dispersing semiconductor, and they essentially end up with the same phase diagram, a superfluid, a degenerate electron-Bose gas, Fermi transition. The density at which this happens is slightly higher, it's 2 times 10 to the 12. The transition temperature is about the same, and really the only difference is the effective masses. Having worked with molybdenum disulfide, I can just say that it's a lot more disordered than bilayer graphene, and even getting to 2 times 10 to the 12 will be a challenge. So, in summary, there is a prediction of excitonic superfluidity. It's been tantalizingly close for as long as I can remember. In gallium arsenide, we need to go to smaller D and lower carrier densities. In monolayer graphene, it hasn't been found either, but we do predict that in bilayer graphene, one can form the superfluid. The suggestion is, by comparison of the mean field calculations with DQMC, that the screening isn't relevant, certainly isn't relevant in the BEC regime because the pairs are just far apart, and the screening turns on only as you approach the BCS regime, but that really happens, that doesn't change things too much. The sample parameters are realistic, they've already been obtained in existing devices, and this approach will work with other thin crystals. So, hopefully, we will one day see the excitonic superfluid in the not too distant future. Thank you.
Thank you for this presentation. Questions?
In normal BCS, electron screening is not very different from your normal system. Here you say it's very different. What is the crucial physics that makes it different.
In normal,
Because the longitudinal response is not very dramatic.
well, here the difference is if you go to large RS, you're in the BEC regime, right?
Yes.
And so screening is completely irrelevant there.
So the key difference is it's the electron-hole pair, not electron-electron pair.
So
What is the difference?
That is it. That's the reason why.
if you have these electron-hole dipoles, right?
Yeah, oh,
The interaction between them is very weak, so there is no Coulomb interaction between them to screen anyway, because the field lines between the electron and holes are just terminating on each other. It's only when they start to come close together that you make the transition to the BCS regime, and then the screening does come in and affects the calculation.
I didn't understand, because you sort of sketched out the BCS calculations, solving the BCS equations, but then you seem to dismiss them and go to Costas-Fowles version of the thing. So what is that BCS calculation irrelevant?
No, the BCS calculation will give you the maximum gap that the superfluid has, right? And so this is the maximum transition temperature. But in 2 dimensions, there's a vortex melting. There's a Kosterlitz-Thouless topological transition, and the system is unstable against that. Again, I think is it vortex anti-vortex pairs form?
Yes.
So that's what limits you. So although the superfluid, if it were a 3-dimensional superfluid, would be stable up to hundreds of Kelvin, in 2 dimensions, there's a Kosterlitz-Thouless transition that prevents you going to such high temperatures.
You're saying the BCS is relevant for 0 temperature?
So
The BCS calculation is relevant for 0 temperature properties?
yeah.
The electric confinement was only included up to a certain level, but in order to get the electron-hole density equal, you have to put gates also, which will also give you additional screening. And they possibly the story less optimistic.
Yes and no. The distance between these 2 layers, if this is only 1 nanometer, and you put the gates, the back gate is 300 nanometers away, and the top gate is 20 nanometers away, almost all of the electric field lines are still going to be running between the electron-hole pairs. So the gates will introduce some screening, but I think it's going to be a very weak perturbation.
Yeah. My question is that you said that the critical temperature is the mean free critical temperature, and then of course you have a Kosterlitz-Thouless transition, so the real critical temperature is lower. But still, I think you can make an estimation of what is this critical temperature in Kosterlitz-Thouless, because if you say that the critical temperature is 500 Kelvin, the mean field, I think you can make an estimation of the Kosterlitz-Thouless transition.
Yeah.
Even you show some expressions. So
we have done.
my question is, what is this Kosterlitz-Thouless critical temperature, more or less?
It's more or less tens of Kelvin.
How much?
Tens of Kelvin.
As in the table, system
Yeah.
A, system B,
Okay,
is the general phase diagram, and below is the numbers.
Okay.
Let me ask a question which is very good one. But this means that essentially you should have a regime
Could
of
you speak up,
fluctuation.
please?
This means that you have a regime of KT fluctuation between room temperature and even if TC goes to 1.
Yeah.
Means that any room temperature measurement should show any paraconductivity or whatever.
Yeah.
That's not C.
That's
Well, no,
it.
no, hang on.
Sorry.
When you say not, in what system is it not
We
seen?
don't know any system
No,
where
that
you
was the
have
question.
a
Is it
variation
that C?
of 100 Kelvin between.
We have to
You would
wait
see,
for
you would see.
the we have to wait for the experiments. But no one has studied dual bilayer graphing. So, but yes, that's the exciting thing. That not only do you have the superfluid at below
You don't
Kelvin.
even have to measure superconductivity. You will see effect to effect. So
Yeah.
you
Yeah,
will
yeah,
see
yeah.
effect. Do you really believe that we have a system we have mean field which is under the
Sorry?
TC which is 10 Kelvin?
No, you can have a very wide Stratogap region with the deviation from Fermi liquid. You will see something later.
That this was calculated in the mean field.
Was sorry the larger the T pairing Yes, of course, without fluctuation at the moment. It's very complicated to insert fluctuation when you have Coulomb pairing. The T-metric structure becomes very complicated.
But that will drive it down.
That may drive this down, but this temperature is so small compared to the gap that essentially it's...
How would you distinguish between the excitonic superfluid system and the excitonic insulator? It's essentially, from the formal point of view, it's exactly the same. High temperature insulator.
Counterflow, for instance?
I would say, yeah, I mean, would drag not tell the difference, does drag not tell the difference between I mean, in quantum Hall you could tell the difference between a quantum Hall insulator and a quantum Hall superfluid.
So it's only experimentally.
I don't think that drug will distinguish. I don't think that drug will distinguish between insulator and
No, but
the counterflow experiment.
The counterflow experiment,
The counterflow, yes.
You pass the current along one layer and then bring it back through the other layer. And if that is...
So it is only...
So you are able to pass a net... There is a current flowing through the system.
And from the theoretical point of view?
It's the same thing, as you said. Just different terms. Maybe I can make a comment, just a perspective on this phase diagram. So this is just, you know, the standard BEC, BCS crossover, except because of the role of long-range interactions, once you get sort of over the top to the maximum TC, then it comes down much more quickly than it will in a system where it's short-range interactions that do it. But it might be, as you've drawn, a first-order phase transition between the superfluid and Fermi liquid. But it's kind of a long-range interaction version of the BEC-BCS crossover.
Actually, one of the questions earlier was very relevant, because in principle one can tune the length scale of the interaction by the gates, right? So if you make the gates rather close, you can actually shut down, you can use the gates to turn the screening off.
Yeah.
Right?
Yeah.
And so then
Maybe.
that could be quite interesting to consider, actually.
I think we are running out of time, so thanks again for this presentation.